Welcome back, chat. Got some aura farming today happening. No cap. Cool. Right? That one's for you, Fredward. Okay, so few distinctions here that I thought we had this taken care of yesterday, but if not, let's make sure we clarify, because based on some of your pictures, I don't think we quite did. If I have, and we're going to think a little bit different just to make sense of this. Okay, let's say that I just have a bucket of water, and I have to put a top on, but I can erase it. You don't need to draw. This is just us talking, okay? That's going to do everything. Hate it. It's because of that. All right, so let's try that again. And it's going to do the same thing. Oh, yeah, cool. So check it out. Hypothetically, we have this bucket of water. Okay, and let's just say it's a really nice amount. So we have 1 liter of water right here. 1 liter. Okay. If I have 1, 2, 3, 4, 5 particles in here, my concentration is 5 per liter. Because I have a liter of space, I have 5 of them in that liter of water. Are you guys okay with that?
Yeah.
Now, if I want to decrease this concentration, but I'm not allowed to take any particles in or out, what do I need to do? If I wanted that to be like, let's say that this is, for example, Kool-Aid that I've made, and it's way too sweet.
Like less concentrate. Add more water.
I could add more water because I can't take out the bits of Kool-Aid, right? But hypothetically, if I added a whole nother liter of water here, all of these will diffuse everywhere, so I still have those same 5 particles, or there's 5, right? Yeah. Still have the same 5 particles, but my concentration just went from 5 per liter to 5 per 2 liters, right? Or if you want this as a calculation, we'll just say 5 per liter or 2.5 per liter is the new concentration. It is way less concentrated at this point in time. Do you guys agree with that?
Yeah.
Okay, just like you could add water to a cup of Kool-Aid that's too sweet, if inside of my cell is too sweet or not sweet enough, or whatever the case is, we want it to be the same sweetness inside and outside. I can't move the sugar though, but what can move easily through cells? In and out, happens through diffusion.
Oh,
Osmosis is what we call it. Diffusion of what in and out of the cell? Water. You're thinking facilitated diffusion, but check it out. If I want these concentrations to be equal, because that's what we strive for, which side needs more water? So if I add more water over here, like we'll do the same thing. Let's say that this is a liter right now. If this were 6 particles per liter, this is 2 particles per liter, right? If I add more water to the end and I do it like this, now I have 6 particles per, I don't know, half a liter, which is twice as strong now. So I can't add more water to the inside, but if I want them to balance, what could I do?
Add it to the out.
Okay, so all that I'm seeing here, this is like my plasma membrane, and it shrinks and grows depending on how much fluid's inside of it. I need a bunch of the water to leave this side so that now this concentration, it's more concentrated inside, but out here it's now less concentrated and they're balanced again. Okay, I can't tell if that's clicking based on your facial expressions. I mean, I wouldn't write down all the words, but I would draw the picture correctly. So the difference between your picture and my picture, Bam Bam, is I couldn't tell how much water was in each side. Same thing with yours, Andrew. When you actually move that cell membrane, like now these concentrations could be the same. They definitely weren't before, but now they could be. So to make this happen, we had to have more water outside the cell, right? So instead of water rushing into the cell or moving into the cell via diffusion, water is moved where?
Outside.
H2O leaves and moves outside, yes, the cell. Okay, in each of these situations, let's just think about further pieces that go on. When I add more water into a cell, and a balloon is an easy example, if I add a bunch of water into the balloon, it gets bigger, it swells in size. What if I take a bunch of the water out of it? Inflates?
Deflates.
It deflates, right? Like now it doesn't have much. So we'll say cell, and instead of just saying deflate, because I don't want to think about it as a balloon, I'm going to use the word shrivel. What's shrivel mean?
Shrink.
Like shrinks, right? Okay. And it might get deformed in this process as well, right? Because I know that balloons do this. This is what is responsible for seawater killing you. Like if you drink a bunch of seawater, there's a lot of salt in it, right? So now your blood, whatever it is that's near all your cells, there's a lot of salt outside. Now, I'm still getting water into my body when I drink salt water, right? But it does dehydrate me. And it's exactly this. If there's a bunch of salt out here, to make the concentrations balanced, every single cell in my body has to ditch a bunch of its water. Now my cells don't have enough water and they're all dehydrated, which means as a whole, I'm now super dehydrated because my cells had to get rid of all their water to maintain this balance. I die now because all of my cells have shriveled up. They no longer function because all of the water winds up leaving. This is what leads to us having issues. The same thing happens with water intoxication going the opposite way, right? We talked about if you drink too much, all your cells become way too inflated. Unfortunately, animal cells, they have a rigid membrane around them, like an egg does, so they can't nicely change size and shape like plant cells do. Okay, does this idea feel better now than it did yesterday? Okay, if I'm feeling hyperglycemic,
You have a lot of sugar in you.
too much sugar, what if I don't have enough?
Then your diet.
Hypo. Challenge question, what if it's just right?
It's like hypercemic.
It's not hypertonic nor hypotonic. It's, gosh, what was that word for congruence transformations in geometry? Is. So the real word is isometry, but isotonic means the same on both sides.
Oh, isotonic.
Yeah, just like an isosceles means the same length on both sides. Cool. All right. So let's see. We have hit diffusion, and then we looked at osmosis. We've talked about isotonic solutions where the balance is already there. We've talked about hypo, where outside of the cell isn't concentrated enough. We've talked about hyper, where the outside of the cell is too concentrated. And those are our three options. Now, when things diffuse, concentrations move. Does it go from high to low or low to high? Try again. High to low. Hot to cold, high energy to low energy. It's how it always happens. Do you guys think you're all the exact same temperature right now?
Yes. No. Probably.
On the inside, we're probably pretty close, right? But our hands, do me a favor. Grab your partner's arm. Let them grab your arm for you. Don't grab yourself because you won't be able to feel it. But just grab arm, not hands, arm. Is one of you colder? Okay, you can tell which one I can't, right? Okay, so right now, out of you, who's warmer? Is it too close to tell?
Yeah, I think it's Fred.
You think you're warmer?
Yeah, he's cooking.
Okay, so if Brent is indeed warmer and Fred's holding his arm, is energy leaving Brent going to Fred, or is Fred's cold energy going to Zed? Which way's the energy flow?
I think I'm here.
You think you're giving your cold energy?
No, he's giving his warm energy because we're all like naturally warm. So
Yeah, it can't go the other way. High to low, hot to cold, high concentration, low concentration. Energy is flowing. If you feel him being warm compared to you,
Yeah.
energy is going toward you, Fred. Who's warmer there?
Bam, bam.
So who's giving away energy in this process?
I'm taking his energy.
If you're warmer, you're not taking his energy.
Now really, look, he's becoming
Nope.
really cool.
Okay. Cool. All right. So that idea that we see with energy, whether it's heat, whatever, it's the same all the time. Do you want to see? Should we do a quick thing to see how long it takes? A couple drops of dye to diffuse. We'll see if it happens throughout the hour. All right. So.
Oh, then we better do like tomorrow.
So we have some colors diffusing over here. The eggs should be ready tomorrow. That we'll do something and we'll leave them overnight just to see what happens. But we should have shell-less eggs for tomorrow. Okay. Now, three types of solutions that we've dealt with: hypo, iso, and hyper. And it's all from the cell, right? Hyper is outside of the cell is too concentrated. Hypo, outside of the cell is not concentrated enough. Iso, they're the same concentration. Yep, so hypo just means low, right? Okay, so as we're looking there, normally things diffuse in a very particular way, right? So maybe there's more salt outside of a cell than inside. But whether it's like table salt that we're talking about or whatever it is, any nutrient or molecule that we could be worried about, is it possible that even though there's more outside the cell, I'd need more of that inside the cell? Like maybe I just actively, like physically need to go opposite of diffusion. The way that nature wants to do it, I have to do something to make this work. So in the situation where we have that happening, we're going to say that this is where we get into that active transport. So what we've seen so far, diffusion and osmosis, those are known as passive transport because we don't have to add any extra energy to make these things move. It just naturally happens because this wants to balance out. In contrast, though, we have this thing called active transport. So we're going to get some fancy words in here, but as long as you guys are like asking when there's something you don't understand, we should be all right. Right off the bat, we're going to define it and just say, hey, active transport is specifically the movement of, I'm going to say particles, with the understanding that when we talk about particles, these could be a bunch of different things. It could be a single atom. It could be a really like a sugar, a single sugar, something like that. But a particle of some sort, whether it's a molecule or a single atom, doesn't matter. So the movement of particles opposite to what we call the diffusion gradient. Now, fancy words. We know what diffusion is, I hope. What's diffusion?
The loss of momentum.
Let's use different language, but I don't hate that.
Like the loss of energy. Like energy.
Not yet. You're thinking about, I'm trying to think of where you're connecting that. What did we say diffusion was yesterday?
Movement of particles.
It's just the movement of particles. So they typically try to balance, right? So when I'm looking and I say this diffusion gradient, do you guys have any idea what I'm talking about?
No.
Okay, so a gradient, all you have to think of is a direction. So, for example, if I have a high concentration here, so we'll just say here's a high concentration, and I lied, I can't do it like that. If I have a high concentration here and a low here, which way does this diffusion happen? High to low or low to high? Normally it wants to go that way, right? Okay, there are situations where maybe I want it to go the opposite direction because I need specific ratios of stuff inside of a cell. So to do that, we'd have to go this way, right? From low to high. That's the opposite. That is all that we're talking about with the diffusion gradient. The normal way diffusion would happen. They want to be balanced, so usually you have to add or subtract from one side. We just do the opposite. Okay, so we do this, and I'm going to get rid of those. Opposite to the diffusion gradient. There's our first little piece. Now, this happens via, and it just means through the use of. So we need to go opposite of diffusion, and we're going to do this via proteins. And these are our transport proteins, and they come in a bunch of different types. But these proteins, I've been calling those doors, I've been calling the proteins and carbons doors, right? We have better language when we talk about active transport. These are commonly called pumps because they're literally pumping stuff in and out of the cell. So we have to have some sort of physical push to make it go against the way that diffusion wants to naturally happen. If you want a quick check, it's getting greener. Slowly, 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 it is getting more blended. Without touching, no mixing. We're going to let it keep rolling. Okay. Now, for this, trying to decide on how hardcore we want to go into this. Gosh, I'm just struggling to remember. What's an ion?
Ionic bond.
So ionic bonds are formed by ions, and those are different than covalent.
Ions like shared bonds.
Sharing is cooperating or covalent. What's the contrast of sharing? Taking or giving, right? One of those two. Which if I give away an electron, I now get a positive charge because I've gotten rid of a negative. Or if I get an extra electron, I now have a negative charge. So I'm a charged particle. So this next one, we're not going to go crazy into the chemistry, but we are going to talk about it. Here we go. We get some fancy language. We have Na plus slash K plus, and very intentional with the capital and lowercase, just so you guys are well aware. Okay, we have the sodium, potassium, and we'll define this. ATPase pump. Okay. Now, when we look at these things, it's super fancy language, and I don't want to just beat the chemistry to death here, just so you guys know, like we've talked a little bit about it, but we do have to make sure we understand what this is saying. By definition, before we start going into what all this stuff is, this thing, and I'm going to use the arrow like this, just so it doesn't look like I'm only pointing to one of these. Okay, the definition of our ATP pump that we see happening here is the active transport pump. Active transport. So it's a protein that's going to wind up going against the gradient to pump. It's an active transport pump found in animal cells. Which means every single cell in your body, are you animals? So careful. We're going to clean this up. We're not monkeys. That's not true in any sense. We're not apes either.
We descend from them, though.
Nope, not quite. So like, we're not in the evolution chapter, but just to hit it real quick, we're not monkeys. We're not apes. We didn't come from monkeys. We didn't come from apes. That is misleading and mispresented. Check it out. If we're looking at this on ape-like thing, and you don't have to jot this. It's just adding in, Fred, because that comment, like not in a bad way. You have some ape-like thing that has characteristics like people and like monkeys. We obviously have a lot of DNA in common. Like we're 99% the same as chimpanzees. Like 99% of our DNA matches. It's crazy. But this is like a long time ago, like 10 million years ago. Okay, from this ape-like thing, if you have a big population, sometimes random mutations happen, right? And we're not doing evolution fully, but like we're going to talk about it real quick. From this ape-like thing, you got things that started to be more like monkeys and apes. So maybe one branch off of this led to monkeys. Now, there's really like a bunch of branches, right? Because there's different types of monkeys, but we're just talking in general. One branch like this might have led to ape. So things like gorillas and things like that. And then another branch from the same thing led to us. We didn't come from monkeys. That's not the right way to word evolution. And it's often presented like that, but it's misleading. We have an ancestor in common. They also evolved alongside of us. It's not like there were just a bunch of monkeys and chimpanzees and then all of a sudden one of them popped out as a human. It didn't happen like that. We branched off long ago, but we're still pretty close evolutionarily speaking. Not our focus.
So we're kind of like siblings, like because like.
I would say, yeah, like I would say probably closer to cousins in that analogy. But yeah, evolutionarily, we have a common ancestor. Just like you're not siblings with your cousins, but you do have a common ancestor. It's called your grandparent. Same idea.
Would you say one thing I've always thought about that? Would everybody like be kind of related?
We are all related.
Yeah, like yeah. That's what I.
Oh yeah.
Like, we're just,
Oh
like,
yeah.
all related, like.
We are all related.
All related.
All of us.
So you're telling
Like
me.
Freddie might just be like a million decade cousin. That's just,
Yep.
that's
So
just Freddie.
hit it, Bam Bam, because I think I know where this question's going.
So you're telling me Cleopatra was my grandma, bro?
I mean, I can't tell you if she was your grandma or not. What I can tell you is we have a lot of people on our planet right now, and nobody knows exactly why it happened. But I'm trying to think of the time. Like 100,000 years ago, there were a lot of humans on the planet. Like nowhere near as many as there are today because we didn't have modern stuff, but there were a lot. Something happened where the whole human population cut down to like 1,000 people. Like there was a point where humans were super close to extinct. So our genetic diversity that we have now is only a result of those 1,000 people that happened to live. Like we had a bottleneck in all of our population where everybody got forced into this one little pool. So out of that, we're all related. Now, most of the time, random people that you meet are not related enough to cause any issues if you were to procreate and like reproduce with them. But obviously there are issues if you procreate and reproduce with people who are close familial ties to you. Was it this class that we talked about European people? About the kings and queens and stuff?
The nobles and stuff?
I'm trying to remember the name. Something Chin, the Jarlsberg Chin.
Yeah,
Okay, that wasn't here. All right. Anyway, we will do evolution if you guys are interested in it. We're going to have to pick and choose what we'll do, but we're going to continue this right now. So, we are animals. not only kind of, we're not apes. Remember, we just had this conversation. We are related to those. In any sense, we are animals. Whether you believe in evolution or not, I don't care. But we're animals. We have animal cells. We're animals. Okay.
Also, our teeth too. Like we have like sharp ends, like what we use for meat. Like I don't know. That's
Indeed.
something
All right. So anyway, about these things, we sometimes have to go opposite of the way that diffusion wants to happen, and to do that requires energy. So all that this pump does is there's a lot of really specific chemistry stuff that's important to us, like in our bodies, whether you care about it or not. Your body needs it. If you're playing sports but you don't drink water, what's another alternative that's okay to drink? Gatorade, because Gatorade has what?
Electrolytes.
What's an electrolyte?
It's the stuff that replenishes.
It's like
That's
sugar.
yeah, like, what's the word? It's like after you work out.
Okay. Do you guys sweat when you work out? And this is gross, but you ever tasted your sweat? Like, not on purpose, but
It just
you
like-
probably have. What's it taste like?
Salty.
Salty. Which means when you sweat, do you lose a bunch of salt?
Yeah.
Now, does your body need salt?
Yeah.
Too much is a bad thing, but too little is a bad thing as well, right? So if your body needs salt, what do you think is in Gatorade?
Salt,
There's
sugar,
salt in it.
water.
That's an electrolyte. Okay, it is there to replenish all this stuff. So quick check, just as a reminder, these things, what all this pump really does is it maintains, what is Na? Natrium is what it stands for. If you were work with the Roman military, you might have gotten paid in this. Because we put it on everything. We might need it. Maybe it's in Gatorade too.
Money, coin.
Wait, there's money in your Gatorade?
Oh.
He said
Wait,
Check the periodic table. I'm not going to tell you. It maintains this Na plus and this one. I need you guys to tell me what these are. Check your periodic tables. They're in your book.
Okay.
Back cover of your text.
Natural.
So, unless you speak Latin, you're not going to give it to me. It's sodium.
Oh.
Natrium, salt, sodium. Okay, this is sodium, and the fact that it has a plus sign on it just means that this is a sodium ion. This is a sodium that has lost a single electron and now has a positive charge. That's it. Okay, what is that? Potassium. So this potassium, based on this single plus up here, how many electrons did it lose?
one.
It lost one because it now has a plus one charge. Okay, these are sodium and potassium ions in your cells. It maintains these in and out of the cell. Now, we're going to get real specific for a second. I'm not going to jot a bunch of it. I'm just going to use the picture that your book has. And as long as everybody's ears and eyes are open, I'm okay. Like, I'm not going to throw a crazy specific chemistry question at you guys. So, check it out. When I think of salt, specifically sodium, I think of nerve cells is what I think of. Because electrolytes, outside of the biological sense, they allow current and electricity to pass through them. That's what an electrolyte is. So salt water lets electricity flow through it really stinking well. Now, for my cells to communicate in my brain, what I have, and we're not like going to go crazy into depth, but do you know what your brain is made of? What sort of cells?
Organ.
So if you had what's a brain doctor called?
The neurologist.
A neurologist. A neuron, a singular neuron, is a brain cell. Now, they're really complex looking, but what winds up happening is they have heads on them as well. And I'm going to draw the picture here. You do not have to draw this, okay? And we'll talk about just one application of why we care so much about these ions. Okay, let's say I have a nerve cell, and they have like these long chains. They're called dendrites. And then if we zoom in on the end of our cell is something like this. And something like this. So there's another nerve cell right here. And they have these long tails that are like wires that come out of it essentially. Now, that cell has to send a nerve signal to make my fingers wiggle. I have to get information across, right? So they don't physically touch each other, but what does happen is there's like some liquid in here, right? And it turns out if you give me a bunch of little sodium ions in here, we have what's called a sodium channel. Okay, We spoke really briefly. Electrolytes in the physics area or chemistry area, they let what pass through it? Electrolytes, what do you think they let pass through? Electricity. So how do you think that this neuron right here communicates via this sodium channel? What do you think it shoots through this little gap? A small electric current that, depending on how it goes, it tells the other cell what to do. And this happens all the way down. Like firing through my body right now, there's electricity going through between each nerve like this that's transforming that idea down. Sodium is responsible for this. Sodium ions, they're electrolytes. It's fundamental. No sodium in your body means your nerves don't do anything. Your nerves don't do anything means no biological processes that are physical function. Your heart doesn't beat, your brain doesn't think, your lungs don't breathe. None of it. Your whole nervous system is dead if you have no sodium.
So bones.
Okay.
Bones are just your structure. Then? They're just kind of like.
No,
your standard-
bones make red blood cells,
Oh.
which we'll get into that as well. Okay, so with this, we're not going to go super hardcore into it. I'm not going to test you on it, but we are going to talk about it. So let's see if I can get a nice picture here. So, a couple things with active transport. And we'll hit it here, and we're nearly done, just so you guys are aware. So we'll get the camera up. Okay, instead of using the word doors and such, is this not plugged in? Open. Ah, all right. Cool. So check it out. Here's our active transport, and we'll just look at it, focus, and we'll get it a little bit brighter. Okay, so I see there's an inside and outside of the cell. Inside, there's more stuff, right? And I'm going to point at the screen. I can do it right here. Focus. Do it. Cool. Inside the cell, do you guys agree, whatever these yellow things are, there's a lot of them? So diffusion would say these things go which way? Is there more concentration inside or outside right now?
Inside.
Way more inside, so they should go outside. Okay. Now, maybe my cell actually just needs this extra thing. So here's that active transport and the pump rather than the door. Notice it opens and this guy fits in. It then closes on this side and it opens on the other side in turn, and now all of a sudden we got it inside against the direction of diffusion, against the gradient. That is active transport. Now, as we get into specifically this sodium-potassium pump, here's another picture of it, and we're going to talk about this. Some things don't love to come in just on their own. So without going too crazy into detail, we see that we have some transport protein here that says, hey, sodium ions, get out of here. And it just pushes them out. And I can see they're outside the cell. Okay, now when I do this, it doesn't show it, but there's a bunch more sodium in here. Now, these sodiums, they want to balance, and I see that, hey, there's now too much outside because I've gotten rid of 3 of them, which means they want to diffuse back in. I've used energy to actively push them out, and now I'm out of concentration. Are you guys squared away with that thought right now? I push sodium out, and now the concentrations are different. The sodium wants to be in because it wants to be balanced, but this protein has pushed it out. Okay, so now these sodiums want to come back in. Okay, however, turns out this happens when something senses that there's a sugar that I need. These sodiums spit out, they stick to the sugar because of the polarity on this sugar molecule. And now, because these sodiums have to go back in to be balanced, but they're stuck to the sugar, what else are they going to drag along with them? The sodiums have to go back in to be balanced, but there's a sugar stuck to them. What goes in there with the sodiums then? Nope, don't even need an element. These sodiums want to be back in. They stick to the sugar. What's going to go back in with them?
With the sugar.
The sugar is going to go back in with them, right? Now that they're stuck and the sodium has to be in there because it wants to balance, it's going to pull the sugar back in. When my cell needs sugar, and this process is crazy that our bodies do this, like life is just crazy in general, right? But it spits out these sodiums stick to the sugar, and then it needs the sodiums back, so it pulls them back in through a different protein. It spits out of balance across the gradient to bond and pull it back in. So we do this, notice we've not taken any of the energy from the sugar. None of it. All the energy that got used was by that first protein to spit out those sodiums. Okay, I get to use the energy from that to bring the sugar in, rather than having to break down the sugar to get it. Do a quick check for me. Diffusion.
I
We're getting there. We're getting there. We still have 15 minutes. Okay, this is a big concept. If I ask a question about this, it will not be super specific. This is one very particular type of pump that we have. One specific active transport protein. Spits sodium out. It sticks to a sugar, pulls sugar and sodium in. That's the basic. Okay. I don't want to talk about the several paragraphs because they go really into the details and stuff. I don't think I care that much. We didn't even talk about the potassium that happened to stay inside. We won't right now. Are you guys okay with that? Sodium spits out of balance. Sodium grabs the sugar, pulls it back in balance. Plus an extra sugar now to fuel my cell. Cool. All right. Cool. Now, for this, we are pretty much there. All of this so far works really well if we want to move something small in, right? Like I can diffuse in and out. I can do water. I can do maybe some sugar molecules through these fancy gates and pumps. You think it's possible that I need something bigger though? Like maybe I have something big that doesn't fit through the door or through the pump, but it still has to be inside the cell. So we have two ways of doing this. The alternative could also be true. Maybe I have like a garbage bag that won't fit through the door, and I need to get rid of it still though. So there's an issue. We have two last little pieces and two definitions. Do you guys hear that?
Shit.
Yeah.
Was it a sigh? It sounded like there was water pumping through the ceiling is what I thought it was. But all right, here we go. Last thing. Moving big particles. Okay. Y'all should write this. We're going to move big particles. And I think we can do this, two definitions, but I think we can make it work with a picture. Do you guys like it when we do stuff with the pictures and talk about it, or do you like the more detailed notes?
Pictures work.
I'm okay with pictures. Hopefully when Jade and RJ watch this, hopefully they actually watch it. Real quickly, don't tell them. If you're watching this video, Jade and RJ, the day you get back, put a note in your phone right now. The day you get back, tell me that I'm the coolest person you've ever met and the Cowboys rock. If you're watching this video and you remember to say that, RJ and Jade will get a prize. When you guys return, if nobody mentions this, everybody else in class gets a prize, except for you two. Cool. This is our check to see if they're watching the video. Do you think they're watching it?
No.
Ooh.
I would say RJ probably wouldn't, but I think.
All right. So we're going to see. Set a reminder because I won't remember. You guys might, but I won't. Put a reminder in your phone, guys. The day you're back, tell me that I'm the coolest and the Cowboys rock. Cool. Prize on the line. All right. So when we're moving big particles, there's two ways that we could do it, right? Into the cell, like we need stuff to enter, or we need stuff to exit. Only two things. So those words fit perfectly. We're going to do two pictures, two definitions. The first one is what we're going to refer to as endocytosis. Okay. Do you think this is entering or exiting? So before that, I'm not going to tell you whether you're right or wrong, Bam Bam. I'm going to draw a picture for endocytosis. The other one that we're going to look at is known as exocytosis. And now I'm going to pose the exact same question. Which one of these are things entering and which one are things exiting? Say that again? Endo is enter or into, right? Okay, endocytosis is how do we move something too big to fit through our pumps inside the cell. And exo is how do we get something too big to leave. Okay, so check it out. I'm going to draw three pictures and three-step process. We're going to talk it through. Let's say step one, and I'm going to use purple for my plasma membrane. Doesn't have to be crazy. Here's a cell. Okay, it's globby, whatever. Good with it. And this cell wants to get this thing inside of it. But it's way too big to fit through any of my transport pumps. Can't do it. Now, if you've ever seen white blood cells attacking something, similar to this. This is what I think of when I see this word. Okay, so it's too big to fit. Now, luckily, this cell, just due to where it lives and how it functions, it has the ability to move around a little bit. Okay, so let's say that it has moved around. I'm going to make this a little bit more bold just so I can see it. let's say that I have my big thing that I want to get inside my cell here. My cell can physically move, and it's going to do the following. It's going to wrap around it like this. Notice, we still have plasma membrane between the cell and whatever that big object is. Now, it is just folded in on itself. If you are struggling to imagine what this looks like, I have string somewhere. I thought I had string somewhere. I can do it with this. Yeah, we'll do it here. So check it out. All right, so I want this pencil inside of this cell, and I'm just going to let this be the boundary of the cell. So here it is. It won't fit in, but check it out. If, and I'm going to have to make this cell bigger because that's a really big object. Okay, so here's my cell, this enclosed area. Okay, if it wraps around like this, has it really gotten it into the cell yet? No, but could it? Is there anything else that it could do to finish this process off? It's got it enclosed now. Now it just has to destroy what? If it destroyed this loop, and that loop just dissolved away, where is that object now?
Oh,
In the cell. It's literally like it ate it almost. So, weird that that one turned on. Will this work now? I think it might. Oh, cool. We don't need no wires. Cool. So, there's step 2. Now, the only thing left blocking me is this right here. This is my plasma membrane. However, if my cell knows that that's the only thing blocking it, and the cell is allowed to do whatever it needs to do, is it possible? Okay, it's not working. I lied. Is it possible that now it just destroys that last little piece of plasma membrane?
Yeah.
And when we destroy that last little piece of plasma membrane, what ends up inside the cell? That big glob, right? Whatever it is. So check it out. We destroyed this part of the membrane. Here's step 3. We now have our cell. It's destroyed that, and that big object is inside. Okay. This is endocytosis. In this picture, if you need to have any sort of explanation, you're probably not using purple. Plasma membrane wraps around and dissolves, and that's, I'm going to put quotations around that because it's just for the sense of this word here. Inner peace. Okay, leaving us with picture 3. So 3-step process. It looks at it, it circles it, it dissolves, and now we're inside. Okay, what if I wanted to exit? Instead of going 1, 2, 3, what would I do?
3, 2, 1.
Exactly. 3 to 2 to 1 based on this picture. We just reverse the process. Circles inside, like pushes it out, does this, and then dissolves that outer layer, and now you have something outside the cell. Cool. That is what I have for 7.3. So, first question, 7.3. This is going to be homework 7.3. Bam Bam's just excited for it. I can hear it. You're going to find this on page 180. I want you to answer 1 through 6. Cool. We have 7 minutes right now. You'll come close to finishing. I don't know that I can see any yellow, but I'm pretty far away. It looks like maybe in the bottom there's a little bit of yellow pooled.
Yeah, like half of it, like this little.
Okay, so here's the deal. I'm not going to touch it until tomorrow, except for right now because I can't leave it sitting here. But I'm really carefully going to pick it up. And I'm intentionally trying not to mix it. I'm not mixing it, I don't think, not like a crazy amount. I'm just going to set it down. We're going to let it continue to diffuse. I might have just mixed it though when I did it. I think I still see a hint of yellow on the bottom. Cool. I want you guys to work on that for now. You probably won't finish all of it right this second, but you'll get a good start. A couple problems.